You. So what is the real? Can I start now? Um, okay, so I think I will start now. Okay, so welcome to the second tech talk on artificial intelligence. So today I'm going to talk about genetic algorithm. So last time, a couple of months ago, I talked about neural network, and today I will talk about a new, very hot topic in the field of artificial intelligence, which is called genetic algorithm. So again, as last time, so the idea of today is to just give a very high level introduction of what genetic algorithm is, and then to show a couple of things that can be done in Pharo. So yeah, a kind of disclaimer. So these slides, I will share these slides later on, but these slides are really made for the tech talk and not made to be understandable when you read that offline. And actually, this is a summary of a lecture that I give at the University of Chile. Okay, so let's begin. So here, this is like a quote that I like very much from Richard Dawkins, a very well-known evolutionary biologist. And yeah, so the fact that life has evolved, for quite a long time, and like that now we have living systems that we have. So this is something that has always fascinated the computer scientists. Understanding whether at least a part of it, part of this extraordinary evolution can be somehow recreated. So, like what are the necessary ingredients that we need to have in the systems to make it evolve is something that people have been working very hard on understanding, like what are the key ingredients that we need to have in order to have a system that evolves over time. So there's been like a lot of efforts, since the 50s or the 60s There has been, plenty of different algorithms and techniques that have been produced. But before we ask, is that okay? Do people hear me? So you need to say yes somehow. Everything is okay? There is a couple of seconds. There is a latency between what I write on the Discord and what you see on YouTube. Yeah, so it seems to be okay. So the font is okay and everything is good. Okay, so people have been thinking very hard on how we can simulate systems that evolve. So this has produced like a family of algorithms called evolution algorithm. So an evolution algorithm, so this is a family of algorithms that actually is something like very simple. So you start here with an initial population. Population could be like, this is a set of individuals, and individuals could be like really anything. It could be like a living, systems, or it could be like an algorithm, or it could be like a text file, or it could be like anything, really anything that makes sense for the purpose that for the purpose of using the evolution algorithm. So the evolution algorithm could be used, to solve some optimization problems that I will give a couple of examples later on. But the idea is that you start with the population, and the population, the initial population is created randomly, so just pure random. And at the first step here, you have a selection. The selection is made on, it selects a part of the population that deserve to live. And the idea is that the selection phase select a part of the population and make normal individuals as the parents. So once you have the parents, then parents can make babies. And this is called the reproduction mechanism. So from the parents, we can create some offspring. And once we have a set of offspring, then these new babies here can be used to replace the initial population. So the idea is that when you perform a cycle here, the population gets better in something. It could be like, if you're talking here about humans, maybe the new population will be about like living better with the pollution and the climate changes, and whereas the great parents probably were not able to not as robust as we are against the population, the pollution, and the actual systems. But that's really the idea of what is an evolution algorithm. So there are plenty of evolution algorithms. People have been computer scientists have been like pretty good at picking some metaphor that you can find in nature and trying to use the algorithm that the nature has produced to solve some particular problems. For example, here you have one famous evolution algorithm is the ant colony optimization. So this is an algorithm, that is useful, for example, to find a particular path in a graph. And then you have some, like the artificial immune system. This is, like when someone gets infected, you have a wound and you have some bacteria that goes into it, and the body reacts in such a way that, to minimize the impact of these bacteria that goes into your body. And this is something like people have been trying to recreate, to simulate those immune systems. And there are, a long list of evolutionary algorithms. So something we have to talk about today is genetic algorithm. So this is an evolutionary algorithm that is very simple and extraordinarily efficient. So maybe we can talk about like genetic programming at the end. I don't know whether we have time or not. But yeah, the idea of today is to talk about genetic algorithm. So genetic algorithm is a kind of evolutionary algorithm. So an evolutionary algorithm, the idea is the following, is that if you have X called a population, and here at the times t plus 1 is equal to the previous population at time t, for which you have made a selection, and then you change something. You change something, and it could be some random variation that you just put in your population. So here, this point equation here says two things very, very important. The first one is that a population is based on, is the result of some operation made on the previous population. And then here you have, so you have two ingredients. The first one is about the selection. So you need to select some individuals of the population, and then you can do something with those selected individuals, and then you can do some random mutations on top of. So this is really a key, equation where most of the evolution algorithm can be expressed. So the evolutionary mechanism have very, plenty of advantages. So I'll move on. So okay, now about genetic algorithm. So genetic algorithm genetic algorithm is a technique that can solve some problems without specifying at all, like what is the form or even the structure of the solution in advance. And so some people say that genetic algorithm is a simulation really of evolution, and they use some biological genetic operation to carry out these evolutions and simulation. So the idea is really not new. I mean, the idea comes from the 60s, and where in the PhD thesis of Bagel, then there was this first idea of simulating the behavior that is happening with what happens in the genes, in the chromosome, how they get mixed, and this is really the essence of his PhD. So genetic algorithm, and as for most evolutionary algorithm, is simply like it can be considered as an optimization method. It means that if you have a function here, if you have a function that takes an element as input and return a real value, a number. So you have a function here that takes an input and return a number. And the idea is x here could be like not just one value, but a set of values. So here we are talking about a tuple. And the idea is genetic algorithm can maximize this function f. So we'll find what are the elements here that you need to provide to f in order to increase the value of f. And and that's all. So one limitation of the genetic algorithm and other evolutionary algorithm is that you cannot really find, you're not sure whether the answer, the result of the algorithm is optimal. That you don't know. But something that you can be sure is that it is maximal for some range at least. So the result given by a genetic algorithm you cannot have any guarantee whether it's optimal or not. However, in many cases it is good enough. So here this is the general chart of a genetic algorithm. So you create here a population here. So you create an initial population, and you need to evaluate the fitness of each of the individual. So it means that here you have, population that is created randomly, and you will have some bad elements and some good elements. So the first step here is for each element of your population, you need to evaluate how good the individual is. So there are many ways to do that. We'll go into details later on. But the idea is that you have a general population with plenty of random individuals, and then you need to assess how good each individual it is. So it could be that you have found a solution to the problem you are trying to solve. So it means that you created some individuals, and maybe one individual is good enough. In that case, then you have solved the problem. Or it could be that you haven't found a solution, so it means that now you need to select part of the population, and this is called the selection mechanism. So there are several ways to do the selection, but the idea is that you pick elements that are the most interesting. So again, if I want like to do that with a metaphor with humans, or with animals, let's say with animals, and then you have some animals, some rabbit that maybe can run the fastest, because you may have a fox that want to eat the rabbit, and you have some population of rabbit, and then the fitness in that case will be how fast the rabbit can run. And maybe you have a rabbit that can escape perfectly the foxes. If not, then you select the fastest rabbit from the population, and then you make them having babies, and then hopefully the element that you will get from the reproduction phase, you need to evaluate again, and then you can create a new population. But that is the general idea. So here this is the using a pseudocode. So you have here the initial population. Then you have a while loop. So you need to do the loop while a particular condition is not fulfilled. So there are many conditions that describe when you should stop the algorithm. You maybe after a given number of generations, or you maybe like if you have found the solution, or maybe if you are very close to the solution you are looking for. So there are many kind of different conditions here you can have. And the loop then is the following. So you need to select some individual for reproductions. Then you need to create the offspring, by crossing the genes of some individuals. And the classical way of doing that is you pick two parents from the current population, and then you cross the genetic information. And then at some point here, also very important, is that you can do some random mutation. You can do some random mutation on some individuals. So both of these two genetic operations are very important. If you remove one, then the system may not work. And then here you can compute the new generation. So first you pick some elements, some relevant element from the current population. You create some offsprings by crossing individuals, and then you do some mutation on the individuals, and then you can create a new generation. So here, let's pick an example. So imagine that you have a friend that give you a challenge. Your friend wrote on a piece of paper, a word made of 3 letters. And then he asks you, okay, you need to find it. Please find my word that I've written down on here secretly on the piece of paper. So the only thing I can tell you is that the word is made of 3 letters. And and then if you give me a word, then I will tell you how many letters are actually correct. So, you can randomly create 3 words. We call it W1, W2, W3, and each word has 3 letters. So so if you give W1 to your friend and tell you, there are 3 letters that are different. So it means that this one, doesn't, is not really interesting because no letters really matches the secret word. And in W2 you may have 2 letters that are different. And in W3, then I might have just 1 letter that is different. So it means that we are actually kind of close to the solution, but we haven't found the solution. But we're kind of close. So it means that the word W2 and W3 are closer to the solution than W1. And so it means that W1 is not really interesting. So we can just it is too far from the secret word that we can just forget it. And so now we will, we have the following option, or we can randomly create a new word, hoping that the word we create will be better than W2 and W3, or you can modify some letters in W2 or W3, hoping that, the thing will improve, or also you can combine W2 and W3 in the hope to have a better sequence, a better word. So, what it means to have a better word. So here, someone is able to tell you how many different letters in a word. If for given words, how many letters are different than for the secret word. It means that we need a function function. Okay, no, I will talk about the function later. It's okay. So the very first step is to initialize the population. So, in that case, we need to create, a number of words made of 3 letters. So it means that the initial size of the population is the parameters. So we can say that n is equal to 10. So at the very beginning, the initial population will be made of 10 words, each word having 3 letters, random. So the second thing is we need to evaluate how good a word is. So the fitness, so this function that tells you how good an individual is called the fitness function. How fit an individual is for, according to the problem we would like to solve. So the fitness function produce, so it return a value, like a number, and that indicates, what is, how good the individual is. So for given individual, then it produces a number, and so it's very important that for the fact that we have this fitness function, we should be able to express a problem that one wants to solve. In that case, define a circuit word, we should be able to express that using a fitness function. And so, assuming that the secret word is cat, C-A-T. So if we have like some words, like call, the fitness function will be 1. The fitness value will be 1 because C is the same. So we found a letter, 1 letter. And we have O and W that are not part of the secret word. So if we have cake, C-A-K, then we have, like a fitness of 2 because we have here like C and A that matches. And then we have the word cat. The word cat, like as a fitness of 3, which is in this case the maximum. It means that, if we have for one individual, if we found a fitness of 3, then it means that we found the solution, and then the algorithm can stop and give the result. Okay, so now in the case that the initial population, we have no words that have the fitness of 3, then we need to do some combination of the word. We need to produce a new population. This population, involved the Darwinian natural selection that have the 3 important ingredients. The first one is heredity. It means that a child receives the properties that are from the parents. Me personally, I have blue eyes because my mother, I have very bright eyes, and my great mother had some blue eyes. So I mean that there are some properties that come from the parents that can give to the children, and this is something like very, very important, that the parents can transmit their property to their child. So then we can have like some variation, and some variation may be introduced randomly in some children. It means that the children, they cannot be the identical copy of their parents. There has to be like some random changes in the genetic information background of each individual, because this is what makes time to times one of these random variation that happens could be tremendous changes that could be highly beneficial. So it's very important to have this variation here. And then here we have the selection, and some member of the population must have like the possibility to be a parents and to have kids. And in that case, having kids in that case means that they should have a chance to transmit their genetical information. So this is, typically called the survival of the fittest. Like the strongest, they will survive, and the strongest, may not be. I mean, in the case of computer science, there is nothing. The strength here may be like how good an individual is to solve a particular problem. So then there is the selection here. So the selection is so once we have the initial population, when we compute the fitness for each individual of that population, then we need to select what are the individuals that are fit enough to become parents. And then there are plenty of strategies that are possible. The first one would be we pick the best 25%. That could be one. Or we could, we could have like the probability to pick a parent that depends on its fitness. For example, if you have individual E1 that has a fitness of 5 and another individual E2 that has a fitness of 10, then maybe, E2 has 2 times more probability to be picked. But there are several algorithms that are available for doing the selection. Even the simple one works, a very simple one, such as, you just pick the best. That works well, but not very, very well. But that is good enough in many, many cases. And then here you have like the mating pool that you can create where you pick, but this is just a detail. So here this is a selection called the roulette. So yeah, here there are some links. So this is a mechanism. This is a simple. Selection mechanism that is this one actually. Here. Yeah, you can read that offline. And then comes the fourth step, which is about the reproduction. So this step is necessary because it creates a new population. The size of the population is constant over the time. So if you start like with an initial population of 10, let's say 10, then over the generation you will always have a population of the same size as the initial population. So this is something that is, like in genetic algorithm, this is something which is constant. So the size of the population is really something constant. There are some other evolutionary algorithms where the population can vary, but in the case of genetic algorithm, it is constant. So yes, so a baby, like a offspring, is created using 2 genetic operations, so called the crossover and mutation. There are some other operations that you can imagine and we will see some of them when we will combine that with neural networks. But in that case, the most classical genetic operations are the crossover and the mutation. So the crossover works that way. So if we pick 2 parents from the population, so the 2 individuals here have the same size. So we need to pick like 1 cutting point. So in that case here, we pick 1 cutting point here. It means that the kids will have the genetical information of that parent until here, and then from the other parents we'll have that part here. So this is how here you can combine 2 genetic information into 1. So randomly you pick a cutting point. Yeah, and that's cutting point is randomly picked. So you can have some constraint. You can for example avoiding some, maybe you can have some particular places where you can have the cutting point. Also, you can prevent the cutting point from being one of the extremity. Could be also. So this is for the first genetic operation, the cutting point. The second one is about the mutation. So here you have an element, and randomly you can change some genes. Randomly you can change some of the value carried out by the genetic information. So this is the second operation. So it means that with what I said, so a number of parameters should emerge. For example, like the mutation rate. So what is the chances that a gene can change? So this is like, what is the probability that here you have this mutation here? So this is one argument, one parameter. So normally this value here is about like 1%. It means that if you have like an individual that has 100 genes, then you will have, statistically, you have 1 mutation per 100 genes. So this is a very common value that is used for that. And then here you have the population size. So it means that the number of individuals to consider at each time. So how large your population is. Then here you have, now it all depends about the problem you are trying to solve. But it could be like 100, 1,000. So most of the times I use genetic algorithm, I use a size like that, between 1,000 and 3,000. And then here you have the number of genes. How many genes contains each individual. Well, that depends on the problem you are trying to solve. So we'll see an example here, but it could be 5. In the case of the words, we have 3. The individuals have 3 letters, so the number of genes that each individual can have is 3. And then here you have the fitness function. The fitness function tells you that how good an individual is, which can be also used to say how far are you from the ideal solution. So the genetic algorithm is a very generic algorithm. You can really use genetic algorithm to, solve many problems. Like finding the shortest path from in a graph, finding some properties, the optimal configuration of a server. I mean, you can really use it like for plenty different range of applications. So it means that the algorithm is very generic. So it means like the balance, so what is hard? Like if you want to use genetic algorithm, so what is the bottleneck here? Well, the bottleneck could be to defining the fitness function. It could be that the fitness function, could be difficult to define. So this is most of the effort you often are spent in defining the fitness function, because this is something that could be not trivial to identify. Or if you have some questions, just ask. We just here. That is the link for the newcomer. Okay. Okay. So then once you provide these parameters, then you can run the algorithm. And you run the algorithm. Often you want to know like how good you did. And often there are 2 metrics that I use to say like how good your your configuration and your algorithm has been strong at identifying a solution. So it could be like for example, one metric could be the number of generations that you need to produce in order to find a solution. It could be like the total times until the solution is found. So there are many metrics that can be used to say how good your parameter is, your configuration is. And yes, so the fitness function, this is something that is not so it's something which is not easy often to identify. And this is I suspect that most of the work goes into the fitness function, because if you have a complex fitness function, maybe your algorithm will not converge into one solution, and this actually happens a lot. Okay, so now here I will show a bit of code. So here this is something that I will put that here. So now here I will do a bit of demo. Okay, so if you take Pharo 6 or Pharo 7, you execute that piece of code here, and this will load this genetic algo here. So this is a small engine that I developed. So I developed it like mainly for research and teaching purposes. So there are some other implementation available that some people from Lille they've been working on also. So this is one, that works relatively well. So so let's pick with an example here. So here this is the font is okay. It's not too small. I can zoom it if you want. Yeah, let me know in the chat if you feel that this is too small. But okay, so here this is a small example. So I will run it. Boom. So this small example here creates here an instance of the class engine. Then you will set the population size. So you will say, I would like my population to have 1,000 individuals. So each individual has 4 genes. 4 genes. So it means that the background, the genetic information carried out by each individual is large of 4. And then here I provide a block that indicates how to create a gene. So the idea is that here I will pick a random, later. So here I do that, So the idea is to pick a normal, a length, to pick randomly a a ladder. So here I'm currently implementing the example that identify the word. And here, like the fitness function takes as an argument the gene. Oh, something I forgot here. Okay, so here I have at random, and here I have a random number. So the idea is that here I provide the random number generator because, yeah, I mean, you want to have a semi-random number generation. So that's why here there is a generator that I can use. And then here the fitness function is the following, is that I want the algorithm to find the word gato, G-A-T-O, which in Spanish means cat. So the idea is that it will count. So the discipline function here takes a collection of genes as an argument, which will be a collection of 4 letters, and then it will make the comparison whether we matches the letter, and we count the number of letters that matches actually. And then we run the thing, and then here we do the inspect. So here in the implementation I provided, you have a graph that shows the evolution of the fitness function. So here the fitness function goes from 0 to 4. It means that 4, this is the maximum because the number of genes is 4. So, well, I mean, in that case, I say the algorithm to run until 10 generation, but I could say like, when to stop earlier. But this is just for example purposes. So at the very beginning, the first individual here has a fitness of 2. Okay. Here there is a fitness of 2. It means that half of the letters in the word are actually correct. And then, here, when we reach 4, then we found the word gato. So here I can see the evolution. So at the very first shot, then we have G-L-T-S. And then, it moves to P-A-T-O. And then G-A-T-O. And then here we found the word. Okay, so we can find, we can have a longer word. So let's say that here I want to find the string hello world. So this is exactly the same thing than before. So here I will run it. And we see that it takes, it's not straight. I mean, here at the very beginning, so here. So it means that here we reach the value of 10. It means that we found the solution. And here we have the evolution of the word that the algorithm is looking for. So, it starts with some random letter until it converges slowly to hello world. Okay, so these were some simple, kind of toy examples. So here at the University of Chile, we have some, we're doing some experiment with robotics, and we are currently planning to use the genetic algorithm to find the path for a robot. So the robot starts somewhere here, I think. So the robot starts somewhere here, and then on the map there is some obstacles, and so these are walls, and the robots need to find a way to exit, which is in the red dot. So the robot need to find a way to exit the maze. And here we have here this is the list of the obstacles, and here I have the beginning points where I need to find the exit, and and then here so here this is the algorithm. So the engine has initial population of 300. Then he said that I want the algorithm to end if the fitness is above 1. Then here I have the mutation rate, which is 1%, and I have a number of genes. So I say 80 because I suspect that, from here to here, I need at least 80 steps. So the gene is produced that way. So it's simply one of the 4 letters, W for west, east, north, and south. So this is one of the 4 letters that the the algorithm that will compute, that will define a gene. A gene is one letter that indicates to which direction the robot needs to move. And then here the fitness, which is the fitness block here, is represent a value that indicates how good a path is to reach the exit. So we know the exit here. We know the position of the exit, which is the endpoint here. So here we do the work because the genes are the sequence of steps. So the genes are the sequence of steps, and the idea is that the fitness is completed by, for the robot to walk all these steps, we see like how far are you from the endpoint. So here we take the distance, using the square root of the distance between the 2 points, and then we do a +1 here, because if we have 0, then we don't want to have an error, because here we do 1 divided. So the genetic algorithm, here it has been defined as it will try to maximize the fitness. And if I want the robot to find the exit, then it should be like very close to the exit. So it means that if I have, the position after doing the work, assuming that I found the exit, so the position after doing the work is the same as endpoint, because the robot finds the exit. So the value here and here will be 0. So that's why I need to add 1. So if the fitness block is 1, it means that I found the exit. And this is what here this point graph here shows. So I can change the configuration. I can say like, 2000 here. I can took. It takes a bit more time, but here I found, okay. So if I have 2000, say if I have a population of 2000 elements, then I just need 2 generations to find the exit. If I have 300, then I need 28 generations. And now, like if I have, let's say, 100. Oh, much more. Oh, so in that case, it doesn't work. So let's try here, 200. Oh. Yeah, I need to play a bit with Okay, so here we found that using 200 populations of 200, then it was not able to find the exit. So here he found something. He found an individual relatively good, but then boom, he lost it. So here there is no way that it can converge. So if here we have 300, then we find the exit. Then here you find the exit. So yeah, so it means that there is a manual effort to identify what is the right configuration of the algorithm. So okay, so so now here we show couple of so here we show a couple of applications. Okay, so this is what I had to say for the theoretical part. So now here we'll give some application, example of application. So here we'll give one example of genetic algorithm used in software engineering to help engineers to find software performance benchmarks. So imagine, okay, so if I give you like here this is a car. So if I ask you like what is the performance of this car, well, I mean you can have an idea, right, of what is, you know, maybe how fast the car can go and what is the acceleration that the car can have. So there are plenty of metrics that one can, you know, me, I don't understand much about cars, but I guess I can give a couple of metrics, you know, like interesting metrics for a car. But for a software, like if here I have a piece of code and I want to know like what is the performance of this source code, well, I mean, this is much more complex. This is much more complex. So people often they write a benchmark to understand, you know, how fast a piece of code can go. So a benchmark is a representative execution of a software system. So this is something which is essential to measure the evolution of performances. So a benchmark requires a workload, and it means that this is some data that the benchmarks need to have in order to produce, you know, to measure the performance. But often this workload is not easy to identify. So here we'll pick an example. So this is an example here given in Java, but the idea is that this piece of code here just take a CSV file and parse it. And the thing is, here I have an example. So here I have an example of, you know, here I have an example of CSV file where I have like 3 numbers per line. And these 3 numbers, you know, can be read by this piece of code here, and then each line is parsed, and each float here as a string is transformed as a real float. But so this is a piece of code that I'm interested to get the feedback, the performance from. Assuming here I have 2 inputs. Inputs 1 where I have 1.1 and 3.0, and 3.2 and 2.0. And here I have like a long float, another long float, another long float. So these files here could be used as a workload. And if I use that piece of code on that code, then I might have different performances. So, and the point here is that if one wants to define a benchmark, then you need to carefully think about which workload one wants to have for that. Because, you know, according to the kind of workload that we provide to the benchmark, I might have very, very different results. For example, like with that code here, with that input files here, I can have like around 5 million numbers per second. If I have that one here, I can have 3 million numbers per second, so which is really different. So this is an example in Java, but I mean, with you know, Neo CSV would be exactly the same thing. And so what we are doing with genetic algorithm is to identify an input file that try to maximize maybe the number of lines or maybe the number of numbers per second that I want to be able to pass. So, so the example of CSV was just an illustrating example. So here I will use an example that I have in Roasal where we use that genetic algorithm to identify, to make the benchmark. So in Roasal, you have the class RTUML class builder, which is a tool to build UML class diagram. So here, if you have a piece of code here, you give it to that class, UML class builder, and boom, you have a UML class diagram. So now the question is like, how many classes per second like it can render? So we use genetic algorithm to answer that question, because of course, you know, like depending to the classes that we provide, we might have different speed, because if you have small classes, it will not be the same thing that having large classes. And we use genetic algorithm to find, you know, to find like what is the range, what is the spectrum of the performance of the class UML class builder. So here the fitness function is the time taken to render 100 classes, 100 genes, and in that class, the genes is one class. So we pick from the random, so we pick like, the pool of gene is all the classes of Pharo. So we pick randomly 100 classes, and we just, and then we draw the UML class diagram, and we measure the times taken to render that class. And then here you can have some, you know, then we, you know, when we reach here, then it means that we find a set of classes that is probably the most interesting, that takes the most time to render. So probably the classes identified here will be the one that takes the most time. And here this is for the low, and now like for the opposite, we find the set of classes that minimize the time taken. So here with that set of classes here, it means that we found the set of classes that were super fast to be rendered by the UML class diagram. So using the genetic algorithm, then we identify the spectrum performances for RTUML class builder. In particular, we found the 100 classes that maximize the performance of the class and the 100 classes that minimize the performance. So this is what we have done. So this is a small example of how we can use genetic algorithm for performance evaluation. So now here I will use other small applications. So yeah, so I will jump back here to the code. So if you remember, like my previous tech talk, on neural network, then I mentioned the fact that neural networks need to learn from examples. Okay, so we have a set of examples, and then the neural networks can learn from those examples, and then you can ask trained neural networks to make some guessing. But there are some situations where you don't have examples. So here I pick one example. So one simple situation where I have the XOR. You know, all 0 XOR 0 equals 0. 0 XOR 1 equal to 1. 1 XOR 0 equal to 1. 1 XOR 1 equal to 0. So if you remember, like my keynote, my tech talk on the neural networks, so that was a problem to solve that needs a neural networks. And so in that case, I create a neural network, and then here I create the genetic algorithm to identify what is the configuration of the neural network to solve the problems. So here I need a particular crossover operation so I will not go to details, but the idea is that the genetic algorithm can find the weight used in the weight and the bias used in the in the neural network. So I can run that, and then I see that the fitness goes into 1. It means that when I have 1, I mean that I have 100% precision. So it means that I'm using a genetic algorithm to build a neural network that is able to reach 100%. So it means that here there is no fitness. There is no learning phase because there is nothing I can learn from. The thing is, I just use genetic algorithm to produce a better neural network that can process better the data. And so here this is a slightly bigger example where I have a neural network that takes 3 inputs, which will be 3 inputs, and we have to convert a binary representation to a decimal number. So if I have 0, 0, 0 is 0, 0, 0, 1 is 1 in binary. So 10 in binary is 2 in decimal. If I have 11 in binary, it's 3 in decimal. And then if I have 111, it's 7. So here I run that. It means that I am creating a neural network that is able to make the conversion between binary to decimal numbers without telling how to do it. And that is really interesting point here. I just create a better neural network that is able to find the decimal number here. So this is like a slightly larger example here. So this kind of techniques of using genetic algorithm to create smart neural networks are used often in the gaming. So here I have a small Pong game. You know, like you remember like the Atari game? So this is an example that has been developed by Milton Mamani and Johnny Cerezo and people working on object profile. So so here I have a small Pong game where I can have some so here I have I can have like small neural networks behind each of these racket here. So currently, like the racket are learning how to play. They don't know really well how to play. So, but they are learning. So each time here there is a failure, then each time there is a failure here, it is learning. So he has learned what he has done wrong. And now here, like the racket are presenting a better behavior. Okay, so here I will give like a couple of examples that I ask my students to work on. So those are topics that if if someone would like to work on, then I will be really happy to help. So the idea is, in the example of the Pong, we've seen how we can create an intelligence that know how to play the Pong game. But we can extend that. We can push that much further. In that case, to have some okay, well, okay, I don't know, that doesn't work. But that is, how can we have some kind of small organism that is able to, to face some challenges. For example, here I can have randomly a car, and and the goal of the car is to, to move, to run fast, and that is. So then we can use genetic algorithm to produce cars that are really fit to go fast. And here also we have another example that where here, go to page, here. So this is here.
In January 2013, I started working on an evolution simulator, but the simulator lay dormant for 2.5 years.
So here this is a small genetic algorithm that shows how...
Muscles have many more traits than nodes, which is its target creatures. Their goal is to run...
Okay, so here we have, we can create a small muscles made of, of edges and nodes. And the idea is that this thing here can jump, can go forward. And the idea is how we can create those muscles here that can, move to a distance. So this is like a very, like compelling example of genetic algorithm where you can help creating some what may appear to be like living systems in order to solve some particular problem. In that case is to go forward and to jump, to be able to jump. Yeah, so this is here a small example here. And yes, so there are several things that can be done regarding like unsupervised learning. So the example that I use with the Pong is to create a neural networks where there is no example here that can be used to learn from. So here I have a small example also that we have been working on is a small snake here that understands that he needs to eat that in order to survive. And yeah, and this is exactly the same thing that I showed you before. Yes, so this is what I wanted to show you today. So the currently like the codes we have shown is not really we haven't made much publicity about the code that I show you, because this is still something that we are working on, and we want to make sure that it reaches like some standards before being released publicly. But this is something that we will do very, very, very soon. Okay, so if there are any questions that I would be really happy to answer, else thank you very much. And yeah, thank you very much. I hope that you got at least like the main idea of what genetic algorithm is good for and how it can be combined, applied to solve some problems. So thank you very much. Bye.